to 10 months of time, this has been completely reabsorbed to the body. And even one of the screws in the magnesium plate, which is found to be a very osteosynthesis material. Osteosynthesis is nothing but which is related to the bone generation. Osteoblast cells is the basic constituent elements or mineral which is involved in your human bone. So it is very osteosynthesis. That means osteoblast cells formation is synthesizing on magnesium plate screws, and there is no irritation or inflammation has been observed during that point of time. But at that point of time, these are the major tackling issue. It was too brittle and the mechanical properties very limited. You cannot achieve a better elongation, better mechanical strength and all. And the one other thing is a very fast degradation. You might have experienced, someone might have experienced, the moment you put the magnesium into any uh, fluid or even exposed to the atmosphere, it starts corroding like anything. So the degradation and corrosion is the two terms. Suppose if a material which is using in the field of biomedical, we will generally call it as degradation. But if we are saying that a material which is going for a general application such as structural or automobile application, we will term that's a corrosion. Both are the meaning of both the terms is similar, like both are removal of material when it is exposed to some kind of environment. And then the problem arises, like, so from that point of time, the researchers being started looking for a better alternative. So the research of magnesium being ceased for a period of time, and then it is started looking into in a bigger way alloying of elements and all. Then that is how the smart implants are evolved. So magnesium implants, we can call it as smart implants that will act according to your physiological environment. So research and advancement in this field. So as I have said, the major drawbacks of having this kind of material is a high degradation rate, and the resorption rate and hydrogen evolution and mechanical integrity loss. So these kind of problem has to be tackled out in terms of the material basically magnesium based alloys when it is put into the physiological environment. The current challenges or R&D direction of this kind of temporary biomaterials goes in the way that you should control the degradation rate. So one of the disadvantage of magnesium alloy is that it is having a higher degradation rate. But this disadvantage we are taking as an advantage in terms of biomedical application. That is the reason magnesium has ideally chosen for biomedical application, because it has to have a degradation, but it should be in controlled nature or tailored nature. So we should make an alloy, or we should think a material which is having a controllable degradation rate with a prolonged mechanical stability and biocompatibility by optimization of what? Its alloy composition and the regulator mechanical property and the microstructural behavior. So this can be achieved by one method is alloying of elements, one is kind of secondary deformation techniques and surface modification. So this is a broad scope of design criteria of magnesium based alloys, something like that. So you can think of an alloying of any element to the system of magnesium, but need to be taken care that it should not create any toxicity. So new alloy system is restricted to ideally choose an alloying element to the biomedical application, keeping the fact in the mind that it should be compactable. And there are a lot many things, like even if you say that mechanical integrity point of, we have 25 different kind of secondary deformation technique, but most of the technique has not been applied in terms of magnesium based alloy, because it is very brittle in nature. So it need to have a specific mechanical deformation technique or secondary deformation technique or plastic deformation techniques need to be developed or need to be overseen for this application. Then the next alternative is to modify the surface modification of this base alloys to tailor the degradation rate. Then collectively these are being seized for a time, and then it's again the interest of bio application of magnesium based alloys renewed in the period of 2000 and 2003 time. And this is a flow diagram of major alloys. You can adopt two kind of alloys. One is currently existing alloys, or it's industrially available alloys, or you can think of modifying it, or you can think of developing your own alloying elements, alloy systems by choosing a right alloying elements. Suppose if you magnesium is can be alloyed with aluminum, magnesium can be alloyed with zinc, manganese, silicon, lithium, calcium, strontium, yttrium. But the thing is that you need to ideally choose whether this kind of alloying element can create any kind of issues to your body. So one of the example I can say that if you add aluminum to the magnesium, it create neurotoxic effects. So you cannot add aluminum in an abundant way to magnesium. But aluminum can improve the mechanical property of the magnesium. So it can be applied to applications such as automobile application. So magnesium can be alloyed with aluminum, but it should be cautiously allowed in terms of biomedical material. There's a new class of alloy system I would like to discuss with you is rare earth element alloys. You must be seen your periodic table 17th group of periodic table. It's a lanthanide series. So you can see that dysprosium, gadolinium, neodymium, lanthanum, cerium. So these are the few rare earth elements are investigated to allowing to magnesium to make an alloy which can be used for biomedical application. But there are studies being saying that you cannot add lanthanum and cerium, it creates some carcinogenic effect. So this is how lanthanum was started and cerium is started. Then later side it stops using lanthanum and cerium because they are saying that it creates some issues with your body. So this is how the timeline of the research of magnesium is taking quite a lot of time to in exploring new alloying elements to understand how it behaves, how the clinical trials, how when it is put into the actual human body and all. So I would like to give a brief of rare earth element alloys. It is a 17th group of elements and it is having a, based on the selection of alloying elements, you need to polish your some of your metallurgical aspects, studies, humidity, roll and all. And you can see that there are not many much researches which is happening in the field of rare earth element alloys specifically for biomedical application. There are very few because I can assure that there are very few. Even people started exploring right and say it's an upcoming area. Those who want to look into this kind of application, this field is an ideal candidate, ideal alloying element can be studied for your later studies if somebody who can interested. And based on the solubility, divide this one is high solid solubility and limited solubility. That means how much of being soluble to the magnesium parametrics. So out of these high solid solubility limits, gadolinium and dysprosium, GD and DY, has been selected as a better alloying element, and there are studies which started looking to alloy with gadolinium and dysprosium. Even neodymium in the limited solid solubility also taken in these studies, proving that there won't be any much issues by using these kind of alloys. And the advantage of using this kind of rare earth element, it is creating a better strengthening. That is a major advantage of using rare earth element. So you must be having a doubt about that. So since it is not our major constituent element, whether it create a toxicity or not, that is what we need to cautiously look, whether this kind of alloying element after combining with magnesium will create any kind of issues or not, need to be overlooked because that is what the later slides explains how can be seen the compatibility issues and how can we how the mechanical property, how the formation of alloying element microstructure and all. So addition of rare earth element which gives a better strengthening by the mechanism of solid solution and precipitation strengthening. So it exhibits, that is one major point need to be remember, it exhibits anti-carcinogenic characteristics. That means there won't be any cancer-causing product will be evolving after a certain period of time of implementation of this alloys. These are the application. Even so, Biotronics is a company. They even developed the cardiovascular stents by using magnesium-based alloys. As I said, this is not being limited to temporary support structure. It can be applied to cardiovascular stent also because you don't need this stent for a longer period of time. Once the clogging is removed by the medicated stent, this stent, we don't need it in your valves. So in that aspect, magnesium is studied and it is being completely or starts degrading after a certain period of implementation. That means your the clogging of blood vessels is completely removed. After that, this kind of stent is being getting degrade slowly and it is completely vanished. You can see it in this image, the JDBM. This is a alloy. This alloy is known as JDBM. It's a combination of rare earth element alloys, and the scientist who is found out this kind of alloy is renamed the JDBM alloy. You can see that this is a stand initial state. After 4 months of time, it starts degrading. You can see the images. It is deviated and it is getting degraded. The size has been even reduced. The other kind of screws, you can see the original screws, and after 18 months of implementation, the screws is completely vanished. But make sure that by that point of time, your bone cells are properly formed if it is using for orthopedic implant application. So we Indians are not very far behind developing of this kind of biomedical application material. You can see that Scalam resistance which is developed in India. The major giants who is offering the stents which is cost around 1 lakhs, and this guy has developed a stent which is cost around 15,000. So that is what. So you can, even if you have a will to do any kind of research, you don't need to stop. This is how the Indian research in the field of biomedical application. And this is what the study which is planned or structured after doing this kind of studies, also previous researches and all. We have formulated a flow diagram of study and how it is being going. The great domain which we are looking this material is biomaterial, and we have developed an alloy. We are trying to develop an alloy which is having a combination of rare earth element addition to the magnesium and forming a magnesium alloys. So to keeping this in mind, that to improve the mechanical property and degradation property. Then the later period of time, you need to control the degradation. That means the tailored degradation property. That means at certain period of time, it should not having any degradation. But after a period of implementation, it should be having a slow degradation. So that time we are looking for an option like surface modification. Once the surface modification alloy has been done, we need to take the sample for various studies. One is like in vitro studies, other is in vivo studies. The studies which I have carried out for this slide, what I am going to tell is that in vitro studies. In vivo study, I will give a introduction about in vivo studies, but I haven't carried out any in vivo studies. Looking off this one, what are the other points we need to take care is that minimum stress shielding effect. As I have told you that since the material which is having a mechanical property matching with the human bone, this is having a minimum stress shielding effect. And the biodegradation. The degradation in biological way, that is what biodegradation. And the minimum gas evolution. Suppose when you put the material into a solution, it is generating a gas. So this kind of gas should not create any inflammatory problems. So you need to have a minimum gas evolution criteria, and it should be having a self medication capacity also. So suppose if you are putting a magnesium alloys into your body, it will support to propagate hydroxyapatite or osteoblast cells formation. So next is it should be compactable, biocompatibility. So we have set the subject of biomedical biomaterials, targeting to get a biomaterial having a tailored mechanical and corrosion properties by using a ways of surface modification. This is how we have envisioned this project. And these are the testing methodologies of biomaterials. What if you say that it's a in vitro and in vivo studies? In vitro is nothing but the experiment or studies which inside the human body or animal body is known as in vitro studies. So what is in vivo? In vivo is nothing but the studies or the experimentation which is happening in ideally chosen animals is known as in vivo studies. You can see that New Zealand rabbits, cats are being even pigs are widely being used for this kind of studies, and finally these animals will be sacrificed. So later in vivo studies, we will be taking this material for clinical trials. And that time we need to ideally choose a human body to do this kind of experimentation. And looking into the other aspect, you need to have a better mechanical property also. So those kind of testing also can be taken care for a biomaterial which is having a better option for temporary implant applications. Coming into the methodology, these are the characterization techniques you need to basically need to understand after your studies, after your mechanical studies or in vivo studies or in vitro studies. One is optical microscope, another is scanning electron microscope with energy dispersive spectroscopy. Even if it is efficient, this is well appreciated. And X-ray diffraction technique, the XRD, and transmission electron microscope (TEM), and atomic absorption spectroscopy for elemental analysis. And the next one is a Fourier transform infrared spectroscopy, is known as FTIR, to understand the oxide formation and hydroxy groups and all. Coming into the methodology of tensile testing, so it is usually followed as per the ASTM E8 standard, and we have looking for an electronic tensometer. Since it is a lightweight material, we have chosen this tensometer. Basically, this machine is used for testing lightweight materials such as aluminum, magnesium-based alloys. And the microviscous hardness tester need to understand the hardness property improvement. And the next is surface roughness measurement in related to wettability behavior. What is wettability? Wettability is nothing but how the material surface behaves with the fluids. Suppose if you dropping a fluid on the surface of your material, how that drop is being placed on the surface, whether it is transmitting or dispersing or it is holding properly on the surface, that also need to be investigated, because the moment you put the material inside your body, your cells surrounding to your tissues, you started getting come to contact with your human come to contact with the implants. That point of time, if it is not having a property of hydrophilicity, it will not adhere on the surface and it will not spread and it will not proliferate. So usually the measurement of angle, you will be dropping a liquid. It's not the diiodomethane and polar liquid and non-polar liquid, even DI water also used. Dropping the liquid on the surface and to understand and to measure the angle between the drop and the surface. If the angle is greater than 90 degree, you can say that it's a hydrophobic. That at that point of time, it does not have any kind of adherence property. If it is less than 90 degree, it is hydrophilic in nature, and is intending that it will it can be cultured on the surface and it can be spread over the surface in a better way by adhering, and the cells can be formed effectively. And the surface roughness measurement, what is the point of using this kind of study? Because what is the surface roughness need to be taken care for this kind of application. Suppose you can see that in the previous slide when I have shown the hip joints, the surface is so rough. That means that the effective cell growth can be promoted in on those kind of stuff. So surface roughness need to be taken care or need to be controlled in certain applications. If the surface roughness is should be in this range, it can the cells can be proliferate or propagate in better way. So next is cytotoxicity study. This is nothing but the investigation of this material create any kind of toxicity to the body. Once you put this kind of material on into your body, any kind of toxic elements are being released to your body or not need to be considered and need to be seen. So MTP assays technique was carried out to understand the cell viability of the alloys, and how we have carried out this one. This is a sample which is used for the studies. As you can see, that there is a 1 centimeter by 1 centimeter samples has been created, even lesser than the zero point 0.5 by zero point 0.5, I guess. And then we have taken a ideal solution, that is the NIH3T3 cell. There are a lot many cells can be available or can be investigated for this application, can be taken for or can be considered for this kind of studies. And once we drop this kind of these samples inside the 24 well plate, the similar way we are seeding this NIH3T3 cells on the surface of the samples, and then we will be keeping this sample for a certain period of time and sampling of 1 day, and after 1 day and 3 days and 5 days, whereas we will fix the frequency of the sampling. And what I have taken in between 1, 3, and 5 days is ideal time which I have selected. And in that same manner, then after that I have seen the surface of the metal. So any kind of cells are formed, or any kind of cells are propagated, or how the degradation need to be also looked in this through the scanning electron micrograph. So this is how the characterization technique comes into picture. So this is the study we have followed. Then we have taken for some analysis to understand what is the cell formation, what is the morphology of cells and all. So I have told you, like, the degradation is the next key domain need to be think of, because once you put the material inside the fluid, the physiological environment is very highly corrosive in nature, because there are a lot many reaction will be started happening because of this reactivity. So the element which is the sample which is putting into the solution, we have to choose an ideal solution that should be mimics to our human fluid. So Hank's balance salt solution is one of the solution I have chosen for this study. And you can see that how, what is the reaction of magnesium. So the moment the magnesium which is reacted, the put it into a solid or liquid, and it reacts with water and generate magnesium hydroxide and hydrogen. Hydrogen is a gas which I have discussed earlier, the gas evolution. So this hydrogen gas need to be evolved control way, otherwise it will definitely create inflammatory reaction on supporting tissue. So there are direct measurement and indirect measurement technique, but indirect measurement is the widely known technique in the field of magnesium based alloy. So that through this indirect measurement, we will be measuring weight loss initial and after the period of time, after a certain period of time. Then we will be monitoring hydrogen evolution, and then we will be monitoring ion release. Ion release nothing but what are the alloying elements we have added to the system, magnesium and the rare earth elements. Whether these ions are releasing in a drastic way or not, that also need to be think of. Then the pH measurement, then the temperature observation. The pH measurement also need to be, because our body pH need to be maintained, and need to see whether this kind of pH is changing or not. If it goes to the high pH, it may create issues with your surrounding tissues. Also the body temperature need to be seen, and these are the indirect measurements. So there are a lot many data will be getting from indirect measurement. Because of that reason, indirect measurement is widely known for magnesium-based alloys. Even I have taken this alloy for direct measurement, normal electrochemical studies, that also displayed, that also presented here, because to make a comparison whether this kind of result can be justified each other or not. And this is a other methodology of finding out degradation studies. And coming into the new field of methodology is a tribo corrosion. This is even just started looking in a different way, and people are studying the corrosion as well as wear. The combination of corrosion and wear are being investigated through tribo corrosion studies. This is having a pin on this tribometer, and which is this is a sample pin on this tribometer, and which is having a fluid environment. So in normal wear testing machine, we will be doing a five-year test, or we will be supplying some kind of fluid medium or coolant medium. So instead of that, the body fluid we will be pouring onto the wear region. So that's why we are combination of wear as well as corrosion is being studied. There are some reputed journal also started publishing in this area, but it's not even established in bigger way, but it is in the upcoming field of studies, tribo corrosion. And later is in vivo studies. Once the in vitro studies are all being done with cytotoxicity and all, so you need to think of a material which is putting into the animal. So that time it's a very stringent procedure to get an approval for doing in vivo studies, because it will be going to an animal body. So ethic committee, the animal committee need to approve your proposal. So animal surgery need to be doing, need to be carried out. So surgery has to be done. So you need to have a better medical practitioner to do this kind of surgery. So that is how it is. So when I think of of writing a proposal to ethic committee. I cannot, uh, being a engineer in the field of mechanical, I cannot sit alone to draft a annual approval draft copy because it needs lot of medical terms, medical. So that is how we call it as is a very highly interdisciplinary area. So collaboration is the only option, or is the broader way of the establishment of your field is a interdisciplinary collaborations. You need to give hand to the medical practitioner and the biomedical people, even doctors and material science engineering people, physics, chemists, there are pharmaceutical people. So this is how. Then surgery need to be done for after choosing a. So once the ethic committee approves, you can carry out in vivo studies. So you need to go and choose an ideal candidate for it. You can rats and pigs and even rabbits and all can be seen for this kind of in vivo studies. Then after putting this one, you need to sample biochemical test. So blood sampling at a certain interval of time will be investigating serum magnesium reaction release, serum creatine, blood urea nitrogen. Oh, these are the critical things need to be seen over a period of time. So how it is being reacted. Then radiographic test. So this where you can see it in the image. The radiographic image, magnesium zinc implants are placed in the femoral shaft, and the bubble formations happen at certain period of time. So you need to understand if this bubble formation is happening or not, or it is being vanished after a certain period of time or not. And then we will be taking histological evolution, the newborn formation and gap between the residual implant and surrounding implants, then in vivo degradation. So doing the in vivo degradation, animals should be sacrificed. That means that this implant has to be taken out from the animal, and you need to take the weights. So this is how you need to understand whether any kind of weight loss has happened. Through this weight loss, we will be measuring the degradation. The similar way, as I have told you, in vitro degradation, not in the experimental setup study, we will be measuring the degradation before placing the implant to the chosen fluid. Then we will be taking the weight of the sample after your period of study. So 180 hours or 240 hours or 5 days, 10 days is the time of immersing this kind of sample into the ideal fluid. So as I have told you, like this is the other kind of surface modification technique I have adopted because I have told you like magnesium development alloy alone cannot give a tailored properties. So you need to either go to secondary deformation technique or you need to go for a surface modification technique. The domain which I have chosen for is surface modification technique. The advantage of this kind of surface modification technique is I'm not adding any new material on the surface of my sample. I am just heating. It's a kind of heat image. I'm just heating the surface of the sample at a high temperature, high by using a high intensity laser beam. This entire setup, which is used for a laser additive manufacturing technique, it's a lens system. This is one of the setup which is available in CSIR, CGCRI, Kolkata. I don't think that any kind of metal additive manufacturing from the lens group is available in India or not. And but even if so, it is very limited. And you can see, and this is the entire setup. There is a small video on that. I will play that and you can see it. I'm not sure this. So this is the glove box inside that additive manufacturing area, and this is how the nozzle. You can see that this is the nozzle. Through the nozzle, the high intensity laser beam is falling on the surface. This is a sample which is fixed on the CNC platform, and this is the surface of the sample after laser metering. You can see the stripes on the surface of the sample. That means that you are not changing the bulk property of the sample. You are just changing the certain level of depth of modification, keeping the things in mind that this is for controlling the degradation. So this is how this surface modification of magnesium alloy works. One more thing, like the major drawback of using magnesium is that it is very explosive in nature. That is the one thing you need to take care, because if it is the magnesium is suddenly exposed to even air, it may catches fire. So you need to think and you need to have utmost cautious to handle this magnesium-based alloys during the formation. I mean, during the casting. Even during the casting, you need to have a separate facility. It should be purged with argon or SF6 purged ambience condition. Otherwise, it will be creating an issue of explosion. You normal ambient condition, you cannot cast magnesium-based alloys. So the similar way, even when you are doing this kind of laser melting also, this glove box should be purged with argon SF6 or kind of nitrogen. Any kind of noble gas need to be purged inside your operation area. So coming into the interpretation and discussion, these are the major references I have taken and used for this discussion. And immediately after the casting, you need to think of this kind of microstructural studies. One of the major advantage of magnesium-based rare earth element alloys, I can say the magnesium zinc gadolinium alloy, that is one of the alloying combination which I have chosen for the study, is that the formation of LPSO. LPSO is nothing but long period stacking ordered phase. If the LPSO phases is formed on this alloy, we can claim that this is having an improved mechanical property. This is the only phase which can only seen in magnesium-based rare earth element alloys. So keeping in the mind that not blindly choosing the element, need to think of this kind of properties also. So formation of LPSO phase has been observed in LP through the TEM analysis. You can see this is a standard in structure and very layered in form and uniformly oriented. And you can see in the SEM microstructure, this black color indicates magnesium phase and the white color in surrounds to that indicates the secondary phase. The major two key points you need to remember from these slides is that uniform distribution of the secondary phase and the LPSO phase. So these are the two formulation properties which will be giving a better property in the later side in terms of mechanical as well as corrosion property. XRD analysis spectra also displayed here to understand the phases. So the mechanical property. So electronic tensometer has been used to understand the mechanical property of this material. And we have seen that there are three alloys we have developed for the studies, and out of that, the quaternary system, magnesium, zinc, gadolinium, neodymium, that means two type combination gives metal mechanical properties. And this is mainly because, as I have told you, the better intermetallic formation, long period stacking phase formation, and the uniform microstructure also. And I have told you, in vitro degradation. This is the degradation which we have studied inside the lab. And these are the three material I can say that magnesium zinc gadolinium and magnesium zinc gadolinium neodymium, magnesium zinc dysprosium. You can see, I have told you like we are observing hydrogen evolution and magnesium ion release. This is not a usual technique which you can see it in the paper, but it is a try for the later studies. We started established this magnesium ion release at equal interval of time. Many people have tried hydrogen evolution, but I haven't seen much studies of magnesium ion release during the degradation, because we have put this sample for 180 hours. You can see in the x-axis it represents exposure time and y-axis even represents the magnesium ion release. So here exposure time versus hydrogen evolution. So we are seeing that this hydrogen evolution supports the cumulative magnesium ion release. So these two things also need to be seen because it should be controlled in way. So this is the direct electrochemical studies I have told you that. So this we have reinvestigated whether these two results are giving a same kind of trend or not. That is what our intention to carry out direct electrochemical studies for this proposed biomaterial. And you have seen that only one thing you need to remember from this slide is that the corrosion rate of these studies has been better for developed magnesium zinc gadolinium. That means 0.99 mm per year weight loss which is happening. And this is also hydrogen evolution through hydrogen evolution and magnesium. So these are the two supporting documents to give what is a weight loss. So we are collecting the data to understand how the corrosion rate or degradation is happening. And the direct chemical studies also given the same kind of trend, even magnesium zinc gadolinium combination having a better corrosion rate. And after that, you need to understand the surface morphology. So what we are trying to do is like, so after immersing the sample onto the fluid for a certain period of time, we are taking the sample and we are directly keeping the sample in the SEM analysis to understand what kind of precipitate, what kind of compounds are formed on the surface, and that formed compounds are feasible for bone cell formation, because once you put the implant onto the body, it will be it will surrounded by tissues and bone cell. So any kind of bone cell formation or bone cell support can be possible or not, or that need to be seen. So SEM analysis, we have found out that these are the EDAX analysis, that means EDS, elemental dispersive spectra analysis carried out to understand what are the elements are distributed. You can see the oxygen, calcium, phosphorus, and these elemental distribution represents that the formation of hydroxyapatite. Hydroxyapatite is a building blocks of your bone cells. This is a major constituent element in your bone. Around 70% of your bone mineral consists of HAP. So we are basically finding out the calcium by phosphate ratio from this EDS analysis. So we got a calcium by phosphorus ratio 1.67, sorry, 1.7, 1.6, 0.67. But this is the minimum level of calcium by phosphate ratio. Suppose need to have a hydroxyapatite formation. Suppose if you get a value of 1.7, that indicates that there is a hydroxyapatite formation. So this will support your material that it can be supporting bone cells formation or better bond bonding. And as I have told you, this is the in vitro cytotoxicity study. So it will give any kind of toxicity is being evolved, or how much is your material is viable to the cells. That is what from your this graphical representation you can see. These are the three investigated alloys in the x-axis and cell viability range in the y-axis. The minimum 70%, that is a cutoff point or the benchmark point. Minimum 70% should be need any material which is going for a biomedical application. So all three alloys which is having a cell viability which is high above than 70%, showing the property that this developed material is viable to the system. And also the cell formation, how the cells are being formed. You can see that in the scanning electron micrography image, the cells are being formed, it's enlarged and flattened. It starts making spread off over the surface and all. These are the cell formation. You can see this is a cell formation. So this creates the feeling that there is a better cell proliferation and cell viability. From this slide, you need to remember that cell viability is crossing the 70%, proving the material status that it can be an ideal partner for biotemporary implant application. And coming into the microstructural studies after laser surface melting. So this is the cross-sectional view after laser surface melting. You can see a melt pool geometry. This geometry is a cup form, cup shaped geometry can be. This is what we are looking for. We have passed high intensity laser beam over the surface, creating a very fine cells. So this kind of fine cellular formation makes the system having a better, that means lesser degradation or controlled degradation. Once this area is lift off to degradation, your substrate will be exposed to. That point of time, we are ensuring that bone cells are effectively formed. So at this point of time, how long this surface is being retained in your body with lesser degradation, the bone cell starts detaching, accumulating. Once it is degraded, it is getting proliferated to the substrate, and by that point of time, the effective formation of cell bone cells or any kind of cells are being formed. So this is what we call it as the very fine cells formation. You can say elongated stream. This is what we usually see through the casting technology, the elongated grains. That means that through the substrate, the heat transfer rate is very more. So towards the substrate, it is elongated in nature, and at the top of the melt pool, it is very fine cells. So by changing the various laser power and velocity, we can control the melt pool geometry and even control the depth of the melt pool geometry. Creates a feeling that how long you need to have sustain this material inside your body. And this is the in vitro degradation studies from after laser surface melting. You can see that the same kind of evolution, hydrogen evolution, is investigated through the 180 hours of immersion of sample. And even magnesium ion release also, the trend of the graph, you can see that very minimal rate of degradation which is happening for this curve. That means this is an ideal candidate for a bioimplant application which is having a controlled degradation. So around 53% of improvement in corrosion or degradation which is observed after surface modification by laser melting. So this is a surface morphology or analysis of corrosion as we have investigated for the previous slides. The same kind of product, same kind of surface has been observed in the same, and these are the mappings. So that is mean that how the elements magnesium, calcium, phosphorus, potassium, sodium are being spread over the surface of the sample after immersion of the sample in the body fluid. So you can say rod-shaped forms of product has been formed, indicating that there is an effective formation of calcium phosphates. So calcium phosphate formation, and again we are converging our conclusion to the hydroxyapatite formation. And this is another studies. Again, you can see that there's a flower-like structures are formed over the surface. These are the corrosion product. You can see it in the semi-image. These white colors are indicating the corrosion products. And you can see that the mapping, you can see that how much intensity the magnesium, the plot or the map is clear to you. So this is a very clustered form of magnesium. The green color indicates magnesium presence. The clustered forms are formed with a high intensity. So very high intensive formation of calcium, phosphorus, potassium and all. Even if one of the other things is if the chlorine formation is much higher in nature in your system, this corrosion will be very rapid. So chlorinated environment or chlorine formation also need to be taken care. And also, it is saying that calcium and phosphate rich phases similar to apatite formation has been observed, and hydroxyapatite formation also confirmed from the studies. And again, you need a number of data to support your conclusion. So again, we are looking for XRD analysis that also gives same kind of phases. The magnesium hydroxide, the formation of magnesium hydroxide will help to control the degradation. That means that is a layer formation which will further stop your corrosion propagation. And the FTIR analysis also give what are the groups are formed. This is phosphate groups and carbonate groups, and phosphate groups formation indicates that calcium phosphate presence. This is a phosphate group. This is the output of FTIR analysis. X-axis is a weight number and y-axis is the transmittance. And this is some studies on laser melted, some that is surface modified samples after corrosion. You can see this is a pit formation. This is a pit formation. I have told you that once the laser melted saw goes off, this is a rapid degradation. When it comes to the substrate, the degradation will be rapid enough. So you can see that in this case, even after 180 hours of immersion, the region is unaffected. That means the degradation is very less. And you can see, here you can see the clustered flower-like structures are formed in the same microstructure, indicates a formation of apatite. And you can see in the figure A, image A, very dense formation of products. These white colors are dense formation of product. That indicates the magnesium hydroxides are formed very effectively and stops the further degradation. You can see the cracks here. These cracks indicate that that layer formation is getting tear off from the surface and corrosion is penetrating through this crack. And this is how not much densely packed layers on the surface. You can see this white color indicates the product formation, that black color indicates surface of the sample. And as I have told you, surface roughness measurement also need to be seen and overlooked in terms of understanding the wettability. This is a drop which is happening over the surface of the laser melted sample or modified sample. You can see the angle which is measured between the drop and surface is greater than 90 degree. It is hydrophobic, less than 90 degree hydrophilic nature. That direct that angle which is formed is again converted into surface energy terms, and better surface energy having a better adherence of self. That means if it is having a better surface energy uh, value or magnitude from your contact angle, which is having a better hydrophilicity. So these are the surface after laser surface melting or surface modification. And then I these are the results which supports the material can be chosen for a biomedical implant application. And later side, I have told you like there is no in vivo studies has been happened in this area because there is a limited access of in vivo facilities that needs quite a lot of time. So I'm trying to explore that opportunities also to getting into the in vivo studies. You need to have, I have told you, there are a long procedure of doing it. So then later side, what are the research and development and future scope can be taken for any people who is interested to come in this field of studies are strengthening mechanism. That means secondary plastic deformation technique. The only one method we have adopted for this study is surface modification. In the surface modification also we have chosen laser surface melting is the one method. Even without adding any foreign material, even you can think of adding some other coating material which furthers the bond cell formation. Even hydroxyapatite coating, there are a lot many coatings also being available or can be also overlooked for this certain application. This is the other kind of secondary deformation technique, strengthening mechanism. Why I have particularly showing this is that this is very simple technique, can be implemented in your university or in your lab itself without investing much. So this is ECAP, equal channel angular process. This is nothing but a setup which is used to plastically deform your materials, and it is proven that, and it is establishing that, it is started establishing that it is creating a better mechanical property. So as you can see, this is a sample. We are keeping the sample here, and by applying a pressure, it is going through a specified geometry, and it is getting out through the exit nozzle. And there are number of passes also can be given according to your study. So you need to optimize how many number of passes are need to be taken to achieve your mechanical properties. This is nothing but the formation. Again, this is nothing but the plastically we are deforming the material to attain a very fine grain structures. You can see number of papers. Even ECAP is very established. That too, even I experienced during my work, and that is how I would like to mention ECAP process. There are other kind of strengthening mechanism also can be seen. Extrusion also can be possible for magnesium based alloys. Uh, then I don't remember, not coming into my mind any other strengthening mechanism, and this one can be seen for your later studies. And the further scope can be explored for resorbable biomedical materials, can be fretting wear studies. One of the major drawbacks of the behavior of wear of magnesium alloys is for kind of fretting wear. Suppose if it is putting the material for a screws application, the kind of wear mechanism can be seen in such kind of application is fretting wear. So you can try doing fretting wear studies. Even I just started doing second year studies in EIT University, but later it did not happen. We just started by the time that concerned researchers who left out from the campus for the higher studies. And so we need to explore where this kind of facilities are being available. And then various in vitro cell interaction. You can choose different kind of cells for in vitro studies. MTTSA and gene expression, ALPSA can be scientifically explored. And then the later, the last and final, not the final, even after this one clinical trial has to be done, is in vivo studies in animals can be carried out before going into the clinical stages. So with this, I would like to um, wind up my presentation, and there are a lot many things even need to discuss in this magnesium field and magnesium biomaterial area. And I hope that the next, like I can start taking the questions if you have something in your mind. And thank you.
Yes, sir. A few questions have been raised from the participants.
Sure, sure.
I will read out the questions one by one. So the
Okay.
first question is, can you comment on the load-bearing capacity and corrosion behavior of magnesium alloy-based implants when compared to titanium alloys by Ridvik?
Okay, okay. By compared, as I have told you, like the degradation point of view, and the moment you put the application for titanium-based alloys and the application of magnesium-based alloys are quite a different in area, because mainly titanium-based alloys are being used for permanent implant application. But this kind of magnesium-based alloys can be, or it is being proposed for temporary implant application. Example like the cardiovascular stents and the bone fracture and all, where the bone regeneration can be happen. In terms of bone fracture, bone regeneration can be happen in certain area, but hip joint and all, you cannot think of replacing the magnesium alloy because it is having a degradation. And the next question, I guess, like in terms of modulus, in elastic modulus of titanium based alloys is very much higher, like around 240 GPa, I guess. And even for our magnesium based alloys, it is a 40 GPa. So using titanium based alloys, that is what the term I have used, stress shielding effect. That means mismatching of mechanical property. As our bone is having a GPA of 20 GPA, elastic modulus of 20 GPA, and 240 GPA is quite a large magnitude. So keeping that in mind, these are the problems, the inflammatory reactions and loosening of implants and all can be anticipated for titanium alloys.
Second
I guess,
question.
yeah,
Second question again from Ridvik. That is
yeah.
magnesium alloys corrosion behavior in SBF medium.
Yeah, SPF medium. Yeah, we have many number of fluid which mimics our body fluid condition. What I experienced is that I have chosen for Hank's balance salt solution. At that point of time, it was well appreciated in the research domain. And again, when coming into the now the next level of studies, I think now people are using Eagles medium and all. And anyway, but the moment you put the alloy into the SPF or HBSS, it starts corroding very fast. So you need to continuously monitor. But at one point of time, the corrosion gets ceased off. So that point of time, you need to see it critically, and you need to ideally choose SBF.
Next question by Father Arun Jose. How do you validate pH behavior of the implant and how do you nullify the possible fluctuation from natural neutral pH setup in biosystem?
Yes. Usually in vitro studies, the pH can be monitored through a pH meter. That can be very possible and very much can be accepted for understanding the pH behavior. So one more thing, like further is asked, like how can we maintain the pH? Because since I have carried out these studies for 180 hours, people are doing this for days and months. So we are definitely sure that the pH is getting changed day by day. You can choose some buffer pH tablets to top up your fluid to maintain the same body pH. That is one alternative can be considered for your studies. That is one option. Then next would be like in the in vivo studies, pH cannot be. It's very difficult to monitor the pH.
Okay,
Uh,
next
uh,
question.
yes, yes.
Again from Father
Yeah.
Arun Joseph itself. That is
Yeah.
whether you are using cell culture or tissue in vitro studies, like any
Second.
cell lines.
Sorry, sorry. Can you repeat the question?
Were you using cell culture or tissue, like any cell lines for your vitro studies?
In vitro studies. Yes,
Yeah.
the cell line which I have chosen for studies, you can see it in this slide. It's a NIH383 fibroblast line, which we have chosen for these studies. You can even choose even the other cell lines also for your studies. It's not restricted to these studies, but this will create a feel that, or this will give a good justification that if it survives or the effective cell formulation with NIH383 cells, it can having a better cell viability.
Okay. Next question again from Father Arinjos itself. Since you want to explore rare earth elements, will
Yes.
its metallurgy process cost serve the purpose of introducing affordable implants? Can you? Okay.
In terms of affordability, what the question, I guess. In terms of affordability, like the moment we are looking this kind of implants for that particular application is not like a less cost applications. So that is a one fact. Even the cardiovascular stents and biomedical implants is not less cost less cost implants. In terms of monetary aspect, we need to overlook because even rare earth element, but we are not abundantly adding this kind of rare earth elements. The amount of addition of rare earth element to the system uh, is very minimal. So you don't have to think of adding and getting much amount of rare earth element to the system because we need to cautiously add. If you add it very high in composition, you cannot offer a less toxic less toxic implants.
Next question. Can you please provide the resource which says minimum 70% of cell viability is required by Ridvike?
Sure, sure. I can share. I can share. So if he can write me mail and I can share the papers.
Okay. Then last question that is by Father Arinjos. Do you have any comment on buffering system of body in brackets while H2 production posing a challenge while using this sort of implants showing corrosion? I think it's a continuation. This is concerned mainly in cardiovascular implants since they pose potential threat to buffering activity of blood.
This here, father is asking to suggest some buffer activants in between the sound good break. That's it. It's not clear.
Yes, yes, you are on the same line. You are on the same line.
Okay, okay. But right now, I haven't had used any kind of active buffer solution for a cardiovascular stents application. That need to be seen. I think I cannot comment on it. The right buffer activant for the specific application.
Because I can I ask?
Yeah, yeah, yeah.
Okay,
Yes.
why I was asking the same question because of you have already told about since this biological system buffering system is very very what do we call very very crucial. So in
Yes.
that kind of times, cardiovascular implants, if you are using with this kind of rare earth elements or something like that, it is very as you were mentioning before. Either you have to take an alternative of using some sort of what do we call buffering medicines or something to top up your buffering system, right?
Yes. Yes. True. True.
So in that kind of cases, this might be going to a very serious issue later in terms.
Yes. Yes.
That's what I was little concerned about this one, especially on the stents case, especially on the cardiovascular stents case and all.
Yes, yes. Because what I have tried, because I haven't top up my solution with any activated buffer solution, because I was continuously monitoring for this application whether what is the magnitude of pH changes over this period of time. So I haven't experienced, or I have, and ideally choose a buffer activant for a particular application. So that is the
Uh,
reason I'm not much. I'm not.
okay, related to the same line, let me ask you, or let me clear my doubt. One case is, how long you have been monitoring for this case, like the longevity of your studies in this one.
So this one actually I have put it for around 180 hours.
Okay, okay,
Yeah.
okay. Thank you.
So after that period of time, it is getting stabilized. That is the one outlet. Even I have tried even for a longer period of time.
Okay, okay. Oh, so you have already validated with longer time, right?
Yes, yes. But
Okay.
keeping that much of time and extracting the data, even the ion release rate and all is so difficult. So the point 180 hours, it starts getting stabilized. So that is the reason I stopped monitoring my, I limited my period of immersion for 180 hours.
Okay, fine.
Yeah, yeah.
Okay. Any questions from audience? Because that was the last question in the chat box. So with that, we are come to the end of this section. And I take this opportunity to thank Dr. Ragesh K. Rajan for accepting our request and for a lively session. It was very informative and interesting regarding the importance in the selection of materials, the factors and properties that affect the selection of materials, its testing and diagnosis, as well as analysis and all. Thank you, sir. Thank you for sharing this valuable information with us. Thank you and have a good day. Now we
Yeah,
are
thank
having
you.
a,
Thank you. Yeah, can I just
yeah,
thank?
sure.
Yeah, thank you. Thank you, Rajagiri School of Engineering and Technology, for inviting me for this talk. And even thanks to Dr. Nivish George, who introduced me for this talk, and then Dr. Ajit and Mr. Akash and Purnima, faculties of RJST, for helping me to this kind of platform of webinar, and they have even spent some time with me for getting clear my doubts on this kind of webinar. And thank you all, thank you participants and whoever asked me a question, and thank you. And if you have any queries, and you can later side, you can contact me. I will share my contact details with um, James Matthews, or someone else who is a coordinator. And thank you.
Okay. Thank you, sir. Now we are
Thank
having
you.
a short break. Next section is on structural characterization of biomaterials by Dr. Sri Kumar, and that will commence at 3:15.
electrospinning unit, we can make polymers or polymer blends as a fiber form in nanoscale. Typically, if you look at a nanofiber mat of a polymer, it will look like this. It is very useful in wound healing applications as well as for scaffold design, and nowadays a lot of interest is shown on electrospinning because they are in nanoscale, so there will be more surface area to volume. We can even incorporate drugs, we can even incorporate growth factors so that cells grow very well. So what is the principle of this? We take a polymer solution here, okay, and the solution comes out through the needle. There is a voltage applied at the needle tip. The solution hits the collector where there is another voltage. So because of the positive and negative, the solution travels and hits the collector. As you can see, this is an aluminum foil collector. So we start collecting the fibers, and we adjust the various parameters to get nanoscale fibers in the collector. So there are many parameters you need to control here. The voltage you are applying here, the distance between the needle tip and the collector plate, and the flow rate of the polymer that's coming out. We can adjust the temperature of this chamber. So all these are parameters which one needs to adjust, and of course the polymer solution itself is there. We need to adjust the composition of that solution so that we end up getting a nanoscale fiber, uniform fibers. There is a control software here which controls the electrospinning unit. Several parameters can be controlled here. For example, the volume of the liquid polymer solution you have taken is given here. The flow rate at which the polymer solution is coming out of the needle is adjusted here. The diameter of the syringe, the duration, how long you want to run it. So this is a flat plate. In case you have a plate which is rotating, it's called a rotating mantle, we can set the speed of the rotating mantle also here, and also we can tell how long we want to run this electrospinning unit also by setting here. Okay, we have to fill the polymer solution in this syringe, which also has a needle. This is not like a doctor's needle because it is blunt, so that the solution can come out when there is an applied voltage. Here again we are planning to make electrospin fibers of polyvinyl alcohol, that is PVA. Okay, we take 5 grams of polyvinyl alcohol of about 140 kilodalton molecular weight in 100 ml water. If you heat it slightly with about 10 to 15 minutes, it completely dissolves. So I am going to take this polymer solution into this syringe. This syringe is filled with PVA solution. We place it here. After placing the needle in the holder and tightening the screws, this is the positive electrode to which the needle is placed. This is the collector plate on which we have aluminum foil for easy removal. Then we place it in the collector and then tighten the screws. And we clamp it with the negative. Let me explain these controllers here. This is a heater in case you want to heat the chamber to a higher temperature. The temperature inside the chamber is displayed here. This switch is for the lamp here. When we are doing electrospinning, we will switch off this and we will use the halogen lamp, which is shown there, okay, because you can see the fibers coming out only through the halogen lamp. And then this switch is for the controller, and this is for the exhaust, because when you are using solvents you need to remove the solvent vapor, and this one is for the setting up of the high voltage system. Okay, so here it displays the voltage and here it displays the current. We set the voltage and current so that we get very fine nano scale size fibers, and also the fibers are loose so that it doesn't sort of bind to each other. Now we switch off this lamp and switch on the halogen lamp, shut the door, and we have to initiate the run through the computer so that the polymer solution starts coming out. Then we adjust the voltage and the current. Run பண்ணி stop. Run. We increase the current little bit and then start increasing the voltage. As you can see, the voltage is increasing.
Current? Increase little, sir. Yes. Now
ஃபார்ம் அது மேலே ஃபார்ம் ஆகிருக்குல்ல. Once we have collected enough fibers, we switch off this machine, we remove the voltage plates, and then we remove the collector slowly, and we can see the deposit of the polymer. We can see the deposit of the polymer nanofibers on this aluminium foil. We can nicely peel it off, as you can see here, from the aluminium foil, and this is a nanofiber of polyvinyl alcohol. If we look under a scanning electron microscope, we should be able to know the diameter of the fiber. It should be in the nano region. So this product can be used for wound healing purposes, burn injuries, and it can also be used as a scaffold material for growing cells of various types.
Welcome to CADMARK World. CADMARK Software, an ISO-certified organization incorporated in 1999, is a specialist engineering company with 15 crores revenue serving 700 customers with energetic certified team. Our mission and vision statement clearly emphasized by providing latest engineering software technologies to customers to build disruptive solutions for betterment of human life by being good stewards of the resources. With 20 years of rich experience, we implement software solutions along with our core services of CAD consulting, professional software training and 3D printing services. CADMARK has emerged as one of the most promising engineering company in India and ready to deliver quality services to our clients. Let's have a look at solutions. CADMARK partnered with global leaders to sell, support and service their solutions to drive customer innovation. We represent Autodesk for drafting and design software like AutoCAD, Inventor and Revit. As a Dassault Systems Platinum partner, we address areas of product design, styling, systems engineering, PLM solutions and realistic simulation. Accelerate performance and increase design productivity in 3D environment, thorough 2D and 3D mouse from 3D connection. Wide range of 3D printing solutions from MakerBot, a Stratasys company using fused deposition modeling. Finally, ExtraCAD, a product developed by CADMARK, help in inspection report automation and ballooning software for AutoCAD and Inventor quickly and accurately. Our esteemed customers are our guiding force. Their valuable feedback helped us to make measurable improvements in our service. CADMARK, India's first partner to sell 3D experience platform of Dassault Systems to VSSE for various successful space missions. Dassault Systems solutions are deployed in Cochin Shipyard for ship design activities while helping to grid analysis of defense equipments. We serve India Kawasaki Motors for their exclusive design of racing bikes in Pune. On the other hand, Hyundai Transys excels in seating and transmission. The world-class audio systems and cockpit design is created by Hyundai Mobis. Taking small steps in life sciences industry, Niemann's uses Simulia for deep brain simulation. Force Healthcare do 3D printing of eye testing machines, while Aster Medis Pro manufacture quality life-saving medical devices. Finally, our nation's pride academic institutions, universities, startup missions, government training centers create next-generation leaders, entrepreneurs and inventors. Our motto is to drive customer delight and grow with our esteemed customers. CADMARK is happy to serve customers if provided with an opportunity. Come and explore our CADMARK world.
So good afternoon all. We are going to begin the last session. And for the last session of the day, we are having with us Dr. Srikumar VM, Assistant Professor, NIT Jaipur. He is the former faculty of Rajagiri School of Engineering and Technology. Regarding his educational qualification, Dr. Srikumar VM completed BE in Metallurgical Engineering from National Institute of Technology, Durgapur, and PhD in Metallurgical and Materials Engineering from Indian Institute of Technology, Kharagpur. He worked as postdoctoral fellow in Deakin University, Australia, and Brunel University, UK. He has 25 technical publications in national and international journals and conference proceedings. So I invite or I hand over the session to Srikumar sir.
Hello. Hello.
Hello, sir. You're audible. You're audible.
That's presentation. You're audible, right? Okay.
Yeah.
Okay. Then I have the presentation. So in the window where I need to click. Normally I see in the mid of the window.
Sir, in the bottom right corner, you have a present now button.
Yeah, present now button.
When you click on that, you can select three options. Either you can share the entire screen, or you can select a window and share the PowerPoint.
Yes, yes.
Okay. Thank you.
Okay. Thank you very much. So, be able to see?
Yes, sir.
You are able to see the presentation, right?
Yes, sir. We can see that.
Okay. Yes. So, good afternoon, everybody. So, first of all, I would like to thank the organizers to give me a chance to present a talk on this FDP. So, it is okay. So it is a great pleasure to join with Rajagiri after 1 year, because it is the place which I worked before, and it's a great. I have a great feeling to join with the people who are my colleagues last year. So I will start with the topic of today's this session. It's a structural characterization of a biomaterial. So I'm sure that you already might have listened 3 intensive lectures on biomaterials, and I'm sure that you might have learned quite a lot about biomaterials, and at least introductory part of the biomaterials. And my duty is to give some outline about the structural characterization. Structure means it's the maybe the physical structure or the microstructure, or regarding the material structures. And I'm not going to any property characterization at this point of time. I'm sure that the previous session might have covered that. So I'm Dr. Sri Kumar, and I worked as a assistant professor at MNIT Jaipur in metallurgical and materials engineering. And basically, I'm a metallurgical engineering researcher, and I was, frankly speaking, I'm not having enough experience with biomaterials. But the moment I accepted this this request from my colleague, and I thought, okay, let's learn something about biomaterials, but as a person from metallurgical background. So what I understood was the biomaterial is not stops with one subject. It is not metal, it is not ceramic, or it is not a pure chemistry, organic or inorganic chemistry, but it is everything. So if you want to learn, if you want to do some research in biomaterials, you have to learn the basic science of all these science, all these streams. So you have to understand metal, ceramics, polymers, and organic and inorganic chemistry. So this is the definition of biomaterial. It's a natural and synthetic material that can be used for different applications such as tissue engineering, bioelectrode, biosensors. Applications are diversified. And biomaterials include a broad class of materials, because after all, biomaterials are going to use for direct to human body or anything related to our biological application. And it's a day-to-day application. We have to say it's a day-to-day application. So biomaterials are diversified in different ways you can define, like metals, polymers, ceramics, composite materials, and each type of materials having its own role to play in biomaterials. Metals, usually there you cannot see metals as such, because it's always as ores and all. So when you have metals, and metal is having some problem with the compatibility with the biological things, but limited applications, we can see not all the metals can be used for the application, but limited applications, like it is quite common nowadays, dental implants where titanium metal is used, and orthopedic fixations and things like that. Polymers is basically organic material, and now they're having more affinity towards the biological cells and all, and it's having its own set of properties, and more biocompatibility and non-corrosive nature. So as a result, this can be used for even more applications it's like a skin, artificial skin, or like a drug delivery devices, where you can directly use this material into the body, and ocular implants is like a where we use ocular implant is in our eye. And the ceramic materials again, like metals, we have bonds, bond replacement, hard bars, dental implants. They have little bit more affected towards the biological environment. And then composite materials, where the combinations of different materials we can apply for the manufacture of biosensors, where in biosensors we can we have to use different combination of metals to satisfy certain properties, electronic properties, and other microelectronic properties, or simultaneously mechanical property as well. And biomaterial evaluations, I don't want to elaborate more in that. We know that 2000 years ago, it was the wood and ivory tooth, ivory and wood teeth were used for the dentistry, and most of the development has happened in the 20th century, where the introduction of new alloys, metals and alloys, as part of the as part of biomaterial, like stainless steel, cobalt, chromium alloys. Then polymer medicine, that is a big jump. And slowly people have started using different combinations of the materials, like polymer metals, and combinations of composite materials for different applications. So when people realized that the demand was increased, and still people are trying to use advanced materials to get better property as biomaterials. So this is material and application, where we have a set of different type of materials, like silicon rubber is used for tubing inside our body, catheters. Then dacron is a vascular graft, it's a graft, vascular graft, the blood vessels we use. Then cellulose, then PMMA, and the hydrogels, which is used for drug delivery. The aerogels, the hydrogels means it's like a highly porous material, where now you can have the drug inside, and it goes to the particular place and it deliver the drug, and with the minimum effort the disease can be cured. Like stainless steel, titanium, alumina, hydroxyapatite, collagen are all largely used for orthopedic applications. This is the universal picture of how in all our all our body. So it is not simply one material like metal or ceramic. Even in one particular place, where you can find multiple materials used for the to satisfy certain applications. Like for example, heart. You take heart, titanium, there are cobalt, chromium alloys. Then like different polymer material. Like that, prosthetic joints, then blood vessels, there are polymer materials are used. Like that, you can list, the list is endless. Examples, again, so what I said, I'm not going into detail about all this. And prosthetic heart valve, already now the biological thing, it is just mimicking the mechanism of the heart valve by using an artificial mechanism. Similarly, lens. A lens is made by polymer. So these are all this big relief for the patients who are suffering from cataract, especially intraocular lens. Then biosensors. Biosensors give you more details about different details about different operations, like the blood pumping or your brain activities, by implanting the biosensors inside our body, and the data can be collected and analyzed, and proper medicine can be given to the patient. Yeah. Okay. So whatever we say, there are two important requirements as a biomaterial. One is biocompatibility, and another one is a biofunctionality. Functionality is nothing but the particular material has to function it should have a specific physical and mechanical characteristics to play the function. And biocompatibility is its stability on a particular environment. Now, bioenvironment, whether it is stable or not, compatible or not, whether the body or tissue can accept the material for a long period of time. So it is the behavior of the material in a living tissue that does not cause adverse effects such as producing toxicity. That's one of the very important aspect where sometimes this toxicity itself can kill a person. Then physiological reactivity and other immunological response. Yes. So next is, as a research point of view, this all the talk will be moving further with a more research point of view. Suppose you are going to develop a biomaterial. What are the techniques you can look for to study more on the biomaterial and get more acceptable results for the final, if you are going for a technological aspect. So how far you can research on it. So that's why do we need a material characterization. So this is one beautiful example. This is a scanning electron microscopy image of a macroporous cellular membrane, where you can find large, they're highly open pores, large pores with the interconnected channels. And the second membrane is there's the same membrane, the same similar membrane having not so high porous material, but having indentations like a 10 microns indentations. And this particular membrane is used as a covering for the pacemaker. And what people found that when you have such sort of structure, design on the membrane, the activity of the body cell to the particular membrane is less. So what's the main advantage of that is pacemaker usually kept inside the is for inside the body, and it has to be used for quite a long time. So once it started making problems, you have to take that machine out. But the problem is usually pacemaker is covered with a certain membrane that will be in touch with the cell, and the cell activity is quite high. Now, so it is very difficult to remove the pacemaker. So it is a big difficult process. So they changed the property of the material, the membrane, and what found that this particular design give them better longevity of the membrane, and cell activity of the particular membrane is quite less. As a result, the operation or the removal of the pacemaker is fast, and it is easy, and it's a relief for the patient. So in order to understand these sort of things, you have to go into the morphology or the structure and so many other scientific aspects of the material. Another thing is the hydrogel, where the drug delivery, the porosity and how the interconnecting channels of this porosity is very important and in order to achieve better drug delivery. So every time you have to look into the microscopes and see how beautifully they are structured, so that the drug can be easily, the particular molecule can easily come out from the cavity. So these sort of things are part of the research and need to be understood seriously. So this is how we can categorize the characterization. See, nothing new in that. All these characterization techniques are already known, and as a biomaterial scientist, you have to look into all these characterization techniques to understand more about the material. Not only the one technique, you have to combine different techniques. For example, crystalline property, where you have thermoplanetary, differential thermal analyzer, and XRD, and the same teaching will be giving you the volatilization of the material. And similarly, particle size. Suppose you are using any biomaterial will be prepared initially in a solution, for example, polymer material, or any other material which need chemical reactions and things like that. You'll be making it as a colloidal solutions. There you'll have different particles having different size from microns to nano size. In that case, you have to understand the particle size and the morphology, shape, and stability of the particles inside the solution. Then the most important part is the structural and chemical analysis, where you have to understand the chemical structure of a different bond. Whether it's a single bond, it's a multiple bond, how the polarity of the material, the molecules, and whether any foreign element is present in the material, and things like that. You have to understand to find out better property or a change in the property. And the morphology. Morphology is again very important, where SEM, TEM, and scanning probe microscopy (SPM) are important, where you cannot find out any other techniques. Imaging technique is very, very important. And first I am going to thermal analytical techniques, where we have 3 techniques, especially 2 techniques, like differential scanning calorimetry and thermogravimetry. Here, all the other techniques, what I said, all are room temperature techniques. But in this case, you are having the material and you are trying to heat the material. You are heating the material to a higher temperature, and look at the property change, the physical and chemical change during the exposure of the sample to higher temperatures. And differential scanning calorimetry and thermogravimetry, what we are trying to understand is evaporation of volatile constituents, absorption and desorption, moisture and other volatile substances, loss of water, oxidation of metals, thermal decomposition, etc., etc., crystallization and glass transition. So you have a big set of material like metal, ceramic, and polymer material. So these are some of the important properties you have to look into. Now, what we are trying to get from this technique is the enthalpy change associated with the reaction mass change of the sample are measured as a function of the sample temperature or time. Here, DSC, differential scanning calorimetry, is a simple technique. You have a vacuum chamber. You can make it any other not only vacuum. You can create an argon atmosphere or nitrogen. It depends. And you have a sample pan. Here you have the sample pan. You have the reference pan having no samples, and you have separate heaters. And what the DSC does is, so you have, say, like a little bit of sample in that, and you are heating from the room temperature to a higher temperature at a particular heating rate. And you know that once the pan started heating up, see, the reference pan will less energy compared to the pan with the sample. It's obvious because it has having some polymer, some sample in it. So it will take the energy to heat its own. Now it's like polymer sample, and you have heaters separately. And every time what this DSC does is during the heating, every time both the machine tries to keep the temperature of both sample pan and reference pan same temperature. That is the basic requirement. The temperature of the sample pan and reference should be same. And suppose there is a reaction like an exothermic or endothermic reaction, there will be suddenly a change in the heat of the sample. There will be acceptance or there will be rejection of the heat with respect to the reaction, and there will be sudden change in the temperature as a result of the reaction. So the supply of the heat by the heaters will be adjusted in such a way that every time the temperature of the reference and the sample will be same. So what you will get is, you can plot the curve like this: heat flow and temperature. And see, this is a crystallization peak where you have an exothermic peak, and you take the area of the peak where you can get the enthalpy of the crystallization, and you know how much material you have used, and you can get the heat flow from the graph, and you can get the temperature at which the crystallization takes place, the onset, and all the other details like melting. You have an endothermic reaction, and you can get the area of the curve. Like that, you can find out the energy of different reactions, and you can get the temperature of the reactions, and you can get the thermal property of the particular material. So this is about the enthalpy or energy calculation. And you have TG along, sometimes you have TG along with the DSC apparatus. Or you can have separate TG apparatus. This is thermogravimetry. You have the sample that is kept in the, sample is kept in the same pan, and it is balanced with the other pan, and the same way you are heating up the sample to a higher temperature, and suppose there is a volatilization take place here. SO4 7H2O, where there will be a volatilization happens. Now this particular graph that shows the a temperature starting from 25 degrees Celsius to 125 degrees Celsius. So you will have now like a 7H2 changes to 6H2, then further it is changed to 0.2H2. Like that, the volatilization, the mass change can be calculated. So like that, you can get the thermal property of the material at a different temperature, the sample at a different heating rate, or you can get the same way, you can heating rate and cooling, heating and cooling at a particular rate, and get the graph, and you can compare heating and cooling rate, the heating and cooling graphs of the particular material, and you can analyze different properties like thermal properties of the materials at a different temperatures, at a different heating or cooling rate. Like that is all about the DSC, and there's a quite similar the technique called a DTA, where this is almost the same, quite similar technique, where you have the sample and the reference, and you have only one heater, and the sample is heated, and you are calculating, you are getting the temperature difference between the sample and the reference. Suppose there is a reaction takes place. So in that case, there is a change in the temperature in the sample, and suddenly a temperature difference will be calculated and is plotted in the graph. So you cannot get the enthalpy of the particular reaction, but you can get the temperature difference. So examples, influence of hot pressing. Usually this is the composite which is studied for that particular particular system is hydroxyapatite PLLA composite material, biomaterial, which is prepared by powder compaction and hot pressing. And somebody try to study the try to understand the properties and crystallization, kinetics and decomposition of the composite using TGA. Then another one, determination of vitamin E stabilized cross-linked acetabular cups crystallinity. This is about the crystallinity study which is carried out for a biomaterial. And next we are going to crystallinity. When we talk about crystallinity, X-ray diffraction is the first one that comes in the mind. X-ray diffraction is the most important method for structural characterization of any material. Here we are talking about biomaterial in a crystalline form. X-ray method is based on X-ray diffusion lattice depending on the scattering of X-rays by the electron density of atoms and molecules, and diffraction maxima is achieved when the scattered rays of crystal planes are in phase, and that obeys the Black's law. We know all this, and X-ray diffraction technique is it can give you information about the structure and identification of the crystals, and many other parameters if it is undergoing any deformation. So the deformation also can be understood by the change in the X-ray diffraction pattern. So this X-ray generator or X-ray tube, you have this is the cathode and this is the anode. You have the cathode is this connected with an extra high tension. And this filament is, when you have either it is heated up to a very high temperature so that the electrons are emitted, thermoionic emission. This tungsten, if you have a tungsten filament, or if you have an anthracium hexaboride, that's for field emission, material. So that particular material you use, and when you apply a very high tension, extra high tension, electrons are generated, and these electrons are bombarded on the copper or any material that is placed as anode, and X-ray beam is generated from the anode. So how it is formed? So you have the fast moving electrons which is moving through the atoms, and when it passes through the nucleus influences the electrons and it diverts, and this inelastic scattering that results the continuous X-ray. Now the energy is released from the electrons and you get a continuous X-ray. And you have characteristic X-ray where you have the electrons which kicks the inertia of the electrons, and other the high energy electron is going to take the position of the vacant position. Then the particular another X-ray or the electromagnetic radiation photons are created. So they are called characteristic X-ray. So this is the graph like relative intensity with respect to the wavelength of characteristics X-ray, and it's a superimposition of continuous X-ray and characteristics X-ray. And this is different the K alpha wavelength of a different material which is used for the X-ray diffractions. See, chromium 2.29 angstrom, iron 1.94 angstrom, and this is copper 1.54 angstroms, which is commonly used for X-ray diffraction techniques. And you have electron beam wavelength, and this is for the comparison where the electron beam in SEM and TEM, we use electron beam as the source of the characterization, where you have an electron beam having a wavelength of 0.0196 angstrom. So you have the X-ray, and the X-ray come in contact with one of the atomic plane, and it reflected back. It reflects back at a particular angle. So incident angle and reflected angle both should be same in order to get the Bragg's diffraction. And you have similar such atomic plane in a crystalline material, and you have an atomic plane, interatomic interplanar distance, which is taken as d. And when suppose two X-ray waves are in phase means both are one is having a crest here and having a crest here. So when you superimpose, you get it is like a addition of two waves. So in that case, you have a larger amplitude and higher intensity, and this, in order to get the Bragg's equation satisfied, this n lambda is equal to 2d sine theta, and you get the diffraction or X-ray diffraction at that particular set of plane, where you can get a higher intensity. And if you have more and more such planes, the intensity of the X-ray waves is increased, and you get a high intensity peak in the X-ray diffraction. So this is in the case of one plane. You have multiple planes. Each plane will have its own diffraction angle, and this angle of different planes are calculated. And it's plotted with respect to intensity of the X-ray beam. Here, this is actually the setup where you have the X-ray tube and you have the transmitted X-ray. You have the incident X-ray and you have a scattered X-ray, reflected X-ray, and you have a detector. And this is the theta angle which is made by the sample surface theta, and you have a 2 theta. This theta is actually not with respect to the sample; it's with respect to the crystallographic plane, and you have 2 theta with respect to the detector. And the detector is it is rotated at different it's in a circular motion, and the X-ray beams, the diffractor beams are collected. The photons are collected by the detector from different angles. This is how you get intensity of the X-ray, and you have 2 theta, and you have the diffracted pattern of different planes. Here, this 111 corresponds. This is actually the X-ray diffraction pattern of aluminum alloy, and you have different each peak corresponds to each crystallographic plane. This is characteristics of that particular material. So suppose you have a different material that will show a different crystallographic X-ray pattern, and that give you the understanding about the crystallographic planes. So diffraction peaks corresponding to crystallographic plane, which is signature of the material crystal structure, and from that you can get the material identification by comparing the standard diffraction data. Biomaterial example, XRD used to investigate qualitative and quantitative composition, size of phases, and degree of crystallinity of biocomposite material. X-ray showed the bioactivity of nano-size hydroxyapatite and can be improved by incorporation of some ions. Here, so you have an XRD, but to understand the presence of CO2 plus, you take the XRD, understand the pattern, diffraction pattern, and find out the compound corresponding to cobalt 2 plus in the HAP lattice. Or the change in the lattice parameter can be understood, and from that you can understand the presence of the foreign material, foreign atoms. Next is the particle size. So in order to understand the initial state of the sample preparations, you have to understand how the particle size of different components. Suppose you have a single particle, or you have a dilute solution having particles of maybe submicron or nano size. Nowadays, most of our research are mainly focused on the influence of nano materials and its property in a different environment. So here, influence of particle size. The particle size influences the solution. A small particle dissolve more rapidly than the large ones. This is the surface area minimization. That's called surface area minimization. Particle size influences the flow property of the powders. When you have the powders in a stack and you are trying to see the flow property of the powders, where the particle size clearly influences. If you want to compare the particles of different size, always suggest having different particles. It's not a single type of particle. Packing factor. To improve the packing factor. Particle size influences the stability of the dispersion. The stability of dispersion, such as suspension, emulsion, depends on the size of the dispersed material, because different characteristics, motions associated, influence of Brownian motion, or influence of Newtonian force, and other like gravity, gravitational force acting on the particles. When you have lower, smaller size of the particle, then that particular settling of the particles is changed, and things like that. Particle size, size distribution, particle surface coating, and surface coating influence on cellular uptake of polymeric nanoparticles. So this is a very important things to be studied. So previously I was talking about the X-ray diffraction, and they're called as wide angle X-ray diffraction, wide angle X-ray scattering. So it is actually done at a very high angle, like normally at 2 theta is like 20 degree, or maybe 18 or 52 or higher angle. Here we are looking for the small angle X-ray scattering, where you can get the size of nanoparticles indirectly. It is not a direct method, but you can get some signature regarding the nanoparticle size, and from different calculations you can understand the size of the particles. A powerful experimental technique that is widely used in material science, structural biology, and so on. It enables the analysis of nanoscale structures and dimension variety of materials, characterization of nanoparticles, colloid, surfactants, proteins, polymers, etc., etc. All these can be studied. Here, these are the two diagrams. This is a wide angle where you have an X-ray source, and you have theta with respect to the sample. and you have 2 theta. And here this is called wide angle X-ray scattering, where the incident X-ray and you have the distance between the sample and detector is something like less than 0.5 meter. In order to get a lower angle, what you have to have is the distance between the sample and detector should be much higher, so that we can get a lower degree. So distance from sample to detector is shorter, and diffraction maxima at larger angles are observed. Small angle usually 0 to 110 degree, and wide angle 10 to 160 degree. So this is the scattering angle. Now usually this is what we have seen so far. So when you go to the lower angle side, you have the sags. So what's the basic theory of sags is, you have an incident beam and you have a transmitted beam. Suppose this is a sample, and you have a refraction, the scattered beam, which is actually detected by the is taken by the detector, and the scattering vector is taken as Q is equal to k prime minus k, where the magnitude of Q is equal to 4 pi sine theta divided by lambda. And from the back law, how we can modify it, like d is equal to lambda divided by 2 sine theta, which is equal to 2 pi by q. So this is a scattering factor. The scattering factor is actually inversely proportional to the d, and q is equal to 4 pi sine theta by lambda. So what's the importance of this is, when you have high q, so now it is more about the intra particle. Now, if the scattering is high, the d will be minimum. So d will be minimum means, so it is going to the distance that is reduced to intraatomic level, interplanar level. And when you have low q, you have interparticle. Interparticles means you can increase the d, and you can get the size of the particles, approximate size of the particles from the at a low q. Low q can be achieved by changing the theta to lower level. So that's how the sags is applied. So what you get here is the intensity of X-rays that is scattered by a given sample must be measured as a function of scattering angle. So you have intensity and you have scattering. Here the scattering factor in close proximity to the direct beam. You know that the 2 theta is always, theta or 2 theta is very close to 0. And sags requires an intense yet tightly collimated X-ray beam. The problem here is when you have an X-ray beam and it is going to be incident. The incident beam is very close to the, it's going to be very parallel to the sample surface. So you will have different disturbances, and it has to be collimated. The X-ray beam should be collimated. Should not be there should not be any more parallel beams, but should be more concentrated. Any sorts of other scattering should be minimized to achieve sufficient sensitivity of weakly scattering samples. So this is a very important parameter, and it is compared to X-ray, it is a slightly complicated technique, but you can get a very good property regarding the particle size. The sags was, yes. So you have intensity. This scattering factor and the intensity, they are related with respect to the radius of the particles, and it is mathematically calculated, can be mathematically calculated, and you can plot the you can find out the particle diameter from the intensity scattering plot, this particular diagram. So this is actually indirect method. You have different mathematical formulations, and use the mathematical formulations and finally reach the determination of particle size. Biomaterial examples, which where the sags is used. Sags is used to determine the change of bond crystallized size and shape during an experimental heating treatment. Crystallized size is quite similar to the particle size. This is a non-destructive technique to obtain important information about size, habit, shape, and arrangement of mineral crystals. Once you have the information about the material, so now the next thing is where it is placed, and you can understand more about the existence of that particular material or the crystals in the whole material. So next is the dynamic light scattering, which is called DLS. Particle size can be determined by measuring the random change in the intensity of light scattered from particle suspension. It measures. So here you have the particles which is in a suspension form, and it measure and interpolate the light scattering up to microsecond. And here you use the light scattering to measure the approximate the size of the particle. It measures real-time intensity, thus measuring the dynamic properties like size distribution, then hydrodynamic radius, then diffusion coefficient. Here the fundamental thing is the Brownian motion is the fundamental of this instrument. We have nano size or very small size particles which are in a Brownian motion. Brownian motion of the particle is random motion due to the bombardment by the solvent molecules around it. So the particles are in Brownian motion. Brownian motion of the particles are related to size. It describes the way in which very small particles move. So here the particle size is not the actual particle size, but it is the size of the moving particle, which is different. This random motion is modeled by Stokes-Einstein equation, where d is equal to kBt 3 pi divided by 3 pi eta dt, where you have the diffusion coefficient, and which is related with the hydrodynamic radius of the particles, not the actual particle. D is the hydrodynamic radius of the particle. The diameter of the sphere that has the same diffusion coefficient as the particle. This is the assumption we take. Now you have the particle dimension. This is the hydrodynamic radius of the particle, which having the same diffusion coefficient. The size of the hypothetical hard sphere diffuses in the same fashion as of the particle being measured. Here you have laser, and the laser beam is passed through the sample cell, and the scattering of the laser beam is measured in microseconds, and you get a graph with respect to the intensity of the light with respect to microseconds, and you take place to place, and like time to time you take the values, the intensity, and you correlate, you find out the diffusion coefficient by a correlation function. Here in this particular figure, what you find is you have a small size and coarse particle and small particle, where you have different characteristics of intensity. And now from this particular graph and from this information from a larger amount of time, where you have a construct correlation function GT of the scattered intensity by this particular equation, and tau is the delay time. We can plot a graph like this. Anyway, eventually you can get the particle diameter by different relationship between the delay time and diffusivity, the diffusion coefficient, and diffusion coefficient we know that is related to the particle size. So like that you can reach the information about the particle diameter. So this is an indirect method. Particles having a size greater than 1000 nanometer are not measured by this method. Size of solid particles are not measured by DLS. So different applications. Hydrodynamic size of the nanoparticles, particle, protein, biomaterials are measured. The stability of the nanoparticles as a function of time is studied. Good for detecting the aggregation of particles. So you record only small sample volume, complete recovery of sample after requirement. Sample preparation is not required for the measurement. So this is all about the DLS techniques, where you have the particles in the larger solutions, and you have now suppose you have solid particles, so the particle size distribution can be achieved by different other methods like sieve analysis, sedimentation method, where you can use the solution and you can get a sedimentation, and different other methods technique get the information about particle size distribution. This uniformity are characteristics for active ingredients in the pharmaceutical product. So important indicator of quality and performance in the area of nanotechnology, proteins, cosmetics. So now everywhere the understanding of the particle size distribution is important. Biomaterial is not exception. The effect of particle size on the kinetics of reaction on final micro and nanostructural features of calcium phosphate cement. And another one, effect of particle size and particle surface coating on the cellular uptake of fluorescent polystyrene nanoparticles and nanoparticles coated with polyvinyl. So wherever you use particles, so particle size distribution is understanding of particle size distribution is important. So next is the most important part, which is the structure and chemical analysis. Surface properties occupied by central place in the biomaterial characterization, since there is a correlation with biological performance of material. Surface properties and properties of interest are chemical structure, hydrophilicity, hydrophobicity, presence of ionic groups, morphology, and topography. So these are some of the important techniques we have to understand and to get the more details about the different materials that we use in the biomaterial. These are the techniques. First one is the zeta potential, then contact angle, FTIR, Raman spectroscopy, then NMR, photo, X-ray photoelectron spectroscopy, mass spectrometry, then ETS and WDX. ETX and WDX. So zeta potential and surface charge represent physical properties which are exhibited by any particle in suspension and immersion that can be optimized using this value. So now in the previous thing, we talked about particle suspension, and here we are talking about the stability of the particles in the suspension, and the knowledge of this property is important in reducing the time to need to produce trial formulation and in prediction of long-term stability. The choice of the method for measuring particle zeta potential is depend on the nature of both particle and suspension formulation, and also the size and concentration of particles. These are some of the examples. Negative zeta potential of this particular composite material is favorable for bond regeneration. Then silicon incorporation into hydroxy induce a decrease in net surface charge and isoelectric point of hydroxy apatite. What is zeta potential? Zeta potential or electrokinetic potential is the interfacial double layer at the location of slippering plane related to the point in the bulk move away from the interface. Here, Nernst potential. This is the first one we may know already. Nernst potential or electrothermodynamic potential is defined as the difference in the potential between actual surface and the electroneutral region of the solution. This is Nernst potential. Here, now you have another layer which is called the interfacial double layer, and you have a slipping plane and the distribution and particular area or the slipping. So the zeta potential is for the moving particle, the particle in the solution. The factors of affecting zeta potential are pH, So initially you have one layer there having the distribution, charge distribution, and this is the zeta potential, and with respect to different pH, you have now positive zeta potential and negative zeta potential, where that represents the positive and negative charge, and you have an isoelectric point where now it means the positive and negative means where the value of zeta potential is 0. So this is about the relation of pH and zeta potential. Here you have, in the similar way, in the DLS techniques, you have a laser and you have a detector, and along with that, what you have is you have the sample having the cell. So this cell actually determines the zeta potential, and the laser beam actually detects the influence of the zeta potential on the particle movement, and finally the correlation, the zeta potential and the particle size and the charge distribution, whatever, all these things are correlated with the different thermodynamic expressions, and finally you can get the zeta potential of the particular solution. So what is the purpose of getting the zeta potential is the stability. This is called DVLO theory. The stability of a colloidal system is determined by the sum of van der Waals attractive and electrical double layer repulsive force that exists between the particles as they approach each other due to Brownian motion they are undergoing. So you need to have a Brownian motion. Along with that, you need to have now a sum of the van der Waals, an attractive and a repulsive force. As a result, the particles never trying to meet and combine, or always they stay separately and in the solution, and you get a stable solution. So this is how the zeta potential is important. So the repulsive, especially the double layer repulsive force, is indirectly in relationship with the zeta potential. So next is the contact angle, which is a very different technique, which is used for biocompatibility of the surface compatibility of different materials, which is directly use the surface
So, sir, you are not audible now.
Some technical issues, we will get back to you.
PPT is not so, sir. PPT is not so. Not so.
Yeah, some technical issues. Yeah, some technical issues. We will rectify it soon. Sorry for the inconvenience, some technical issues.